All right, thank you so much, everyone, for joining us for this installment of the Berkeley AI Risk Speaker Series. This time, we're thrilled to have Stuart Russell from UC Berkeley Computer Science joining us. Stuart is the founder of the Center for Human Compatible AI here at Berkeley, and also of the International Association for Safety and Ethics of AI Research.
Safe and Ethical AI.
Safe and Ethical AI. He's been a giant of this field for many years, and he's going to give a talk today on what is to be done about AI. So, Stuart, over to you.
Okay, thank you. How long should I aim for?
If you can go for about, say, 45 minutes, and then we'll have a Q&A afterward.
Okay, I'll try.
There are a lot of questions during the talk.
All right.
Feel free to talk.
All right. So last time I gave this talk was in Delhi a few weeks ago, and it actually ran long. So I will go through it quickly. I will solve that problem. Okay. So AI has been around for a long time. It's about making intelligent machines. For most of the history of the field, we worked within what I've started calling the standard model. So we try to create machines that exhibit rational behavior with respect to objectives. They take actions that can be expected to achieve their objectives. And traditionally, these have been human-specified objectives. We developed lots of technology along the way: search algorithms, reinforcement learning algorithms, MDP solvers, planning systems, et cetera, but all with the same basic framework. You've got optimizing machinery, and you plug in some objective, and then off it goes, solves the problem, and maybe carries out the solution. And this is true not just of AI, but I think a lot of other fields: statistics, operations research, control theory, economics, right? They all kind of work on the same basic paradigm. But AI has this kind of uniquely ambitious, arrogant, depending on how you look at it, objective of being able to do that in a sort of completely general sense. We don't really know what completely general means, but we mean certainly anything that human beings can do, anything that we can learn to do in any environment. We would like machines to be able to do that just as well, if not better. And nowadays, people call this AGI, or artificial general intelligence. For a long time, this was actually the goal of the field. You can go back and look at people in the 50s, and they were quite explicit that this is what we're going to try to do. So this is an interesting question: have we succeeded? Which even 5 years ago, no one would have such a question in their talk, right? But last year, I think it was now, 23. My co-author on my textbook, Peter Norvig, and Blaise, who has a complicated last name, wrote a paper basically saying, yeah, we have succeeded. We have AGI. And they're pretty knowledgeable people. And what they meant was we have AGI in the same sense that when the Wright brothers demonstrated their airplane, we had airplanes. And yeah, the airplanes got bigger, and they have better catering than the Wright brothers did. But it's the same basic principle, that the rest was engineering improvements, and we didn't need to have a major conceptual breakthrough. Now, you could argue that the jet was a breakthrough relative to the propeller, but it's a small quantitative improvement in practice. So this is the argument that they're making. I think this is false, and I'll explain why. I think there's still a lot missing, and and I think the GPT-like models are fundamentally limited in what they can do for for technical reasons, and we also see this in practice. The puzzling thing is that, you know, unlike like a bit, you know, before the Wright brothers, it's like, okay, we know how to make gliders, but we don't know how to make them, you know, go fast for a long time. You know, they just rely on air currents and gravity. And then someone said, oh, okay, well, what's missing is, you know, some kind of propulsive force. You know, we could think about what that might look like. And then along came the internal combustion engine and say, hey, we could put one of those on one of these, and then it would go. So they knew what was missing, and they would sort of, you know, propulsion-shaped gap, and then they filled it with propulsion. But with these kinds of these GPTs, we don't really know how they work. So we don't really know what's missing, and we don't know how to fix it. So it's just a weird situation. It's kind of like when cavemen discovered that if you leave fruit out for a few weeks and drink it, you get really drunk, and it's great. They didn't really understand what was wrong or what was right and what was going on or anything, but you know, I'm sure there was a big boom of investment in, you know, in this newly discovered process, even though they didn't know what it was. So this is an unusual situation in engineering disciplines. So let me talk a little bit about why I think these systems are fundamentally limited, which is, it's not rocket science. So large language models are fixed depth feed-forward circuits, meaning the input, in this case, the sequence of tokens in the context window, goes into the circuit, and it goes through the layers of the circuit, and out the end comes the next token. And the amount of computation that happens is fixed, regardless of how difficult it is to figure out what the answer, the next thing should be, right? And so, you know, there are many cases where to get the next token right, you're going to have to solve a potentially very, very complicated problem, like an NP-hard problem. So if the input is a satisfiability problem, and then you say, you know, and the answer is, you know, yes or no, question mark, and it's supposed to say yes or no, right? It can't output that next token unless it does an exponential amount of work. It can only do an exponential amount of work if the circuit is exponentially large with respect to the input, right? So even though satisfiability is a very simple concept, right? I can write a satisfiability solver in Python in 15 lines, 20 lines, or something like that. It's a simple concept. Because we're only able to use a feed-forward circuit here, it gets turned into an enormous computational representation. And that means that you know, you've got very large circuits with very large numbers of parameters. So even to learn simple concepts, you end up with enormous sample complexity. The amount of data you need to learn those concepts is vast. And in practice, we don't build a circuit that big, and the circuits end up learning sort of piecemeal approximations, sort of fragmentary, inefficient representations of certain concepts that don't capture the generalizations that you would expect them to capture at all. So let me illustrate that with something that, you know, most people, so how many people think that computer Go programs are much better than human beings? Okay, you're wrong. All right, and I'll show you. Because in fact, they haven't learned the most basic concept in Go. So in Go, as you can see, there's black and white stones on a grid. And you can probably also see that they try to join those stones into groups that are connected vertically and horizontally. And so the fundamental concept in Go is the group of stones. So that's a graph connectivity question. And we know from theory that fixed depth feed-forward circuits don't represent graph connectivity correctly. And just think about it, right? It's a 3-line Python program. How big would the circuit have to be to correctly recognize for any pair of locations on this 19 by 19 grid, are those two stones connected to each other? Just think, I'm going to give you a pile of Boolean gates and you get to wire up the circuit, right? How big is it? It's probably millions of gates, right? With millions of parameters. And so it's going to take you millions of examples to learn it. And in fact, it seems like the programs haven't learned it. So let me illustrate that with a game between Kellen Pellerine, who's, or was at the time, a grad student at Montreal who was working in our extended research group. And he's a good amateur Go player, rating about 2,300. The best humans are rated around 3,800. And the best program at that time was this one, JBX Kata 005 or Kata Go, with a rating of about 5,200. So massively superhuman, right? And everyone thought that, you know, the Go programs have just left human beings behind in the dust, and we don't even understand what they're doing. And Kellen is going to give Kata Go a 9-stone handicap, meaning that the computer gets to start the game with 9 stones on the board like that, right? Which makes it pretty easy to win, right? You're just, in Go, you're just trying to surround territory and surround your opponent's pieces, and that's it. It's very simple. If you start with all those stones on the board, it's hard to imagine how you could even lose, but it does. So, and this is a big insult, right? This is, you know, if Kata Go was a 5-year-old learning to play, right, you might give it a 9-stone handicap, but it's this massively superhuman program. So what's going on? Well, let me just show you the game. So keep an eye on what's happening in the bottom right quadrant, right? And so starting around now, right, white starts to make a little group of stones, and then black quickly surrounds it, right, to stop it from growing. And then white starts to surround the black group. So we're making kind of circular sandwich here. And black just allows white to surround those stones, has many, many, many opportunities to rescue them, and it just leaves white to completely surround all those stones and then kill them. And then so black loses the game. That poof, so they're gone. So, you know, and Kellen did this 15 times in a row, and then he also played all the other leading programs, and they all fail in the same way. They have all failed to learn the notion of connectedness correctly, and it seems to be something to do with it being in a circle. Maybe it keeps going around the circle and miscounts how many empty spaces there are because it doesn't remember where it started and just goes around, or maybe it just doesn't understand that this is a group, or who knows what's going on really, but it's not learning the things correctly, and so it doesn't know how to play Go properly. So there you go. All right, so I think the companies that are developing this stuff realized this several years ago, and they are pursuing other methods beyond just making the circuits bigger and bigger and training on more and more data. They are, for example, wrapping an algorithmic loop around the large language model called a large reasoning model, which invokes that large language model many, many times, so that whereas you previously might have needed an exponentially large circuit to solve a hard problem, instead, you can keep the small circuit, but just invoke it many, many times instead. And this is actually, of course, what people do, right? Some stuff we do instantaneously, and some stuff we have to think hard, right? And this is really important fundamental trade-off between computational runtime, computational expense, and the amount of data you need to learn with. And we kind of ignored that trade-off in machine learning because we've pretty much only focused on learning stuff that has either sort of constant or linear size computational requirements at runtime. And I think this was a big mistake because there's just tons of stuff that you can't learn in those representations for simple mathematical reasons. Anyway, so I think the question is open as to whether we're going to succeed. I mean, you know, Sam Altman says we already know how to do AGI. I think he's lying. Dario Amodei says, well, we don't know how to do it, but we will soon, maybe as soon as next year, 2026. You know, one of the reasons is just extrapolating of these scaling laws, where you talk about how much compute, how much data, and then what kind of performance. And this is from Leopold Aschenbrenner's situational awareness, which is a very long and detailed assessment of where we are and then projecting forward in time and warning people that something very serious is coming down the pipe. And notice that, well, you probably can't read it, but in the top right, that's where automated AI research kicks in. So rather than people having to do all this work, the AI systems themselves start doing the nitty-gritty AI research of, you know, how do we scale up these circuits? How do we pre-filter the training data to make it more efficient? How do we improve the computational efficiency of the machine learning algorithms, et cetera, et cetera, et cetera. And most of these sort of quantitative predictions are saying, yeah, we'll get there by 2030, if not before. And you know, there are many people who work in these companies whose opinions I respect, and they all pretty much think it's happening. I mean, there are a few exceptions, but you know, very serious, very brilliant people who think this is happening before 2030. And you know, one simple reason is that the budget for this is out of date, actually. You know, when I wrote this slide, it was 25 times bigger than the annual budget of the Manhattan Project. It's now maybe 50 times bigger, or 500 times bigger than the Large Hadron Collider budget, which is the biggest scientific instrument we've ever built. So maybe this is the biggest technology project in the history of the human race by far. They have really smart people, and they're trying many other ideas. You know, the large reasoning models that I talked about. You know, now I'm hearing, looking at, you know, hierarchical look ahead and so on. So a lot of things that they're basically borrowing from the classical period of AI, but reusing in this new context. So it might not happen, at least not yet. It might be that, you know, they're still pretty much focused on deep learning, on these large circuits as the thing that you train. We've pretty much run out of real data. So there's almost no high quality text left in the universe. If they don't deliver fairly soon, the bubble might burst, right? So these levels of investment are unsustainable unless they deliver substantially higher capabilities than currently exist. And now every day in the Wall Street Journal and Financial Times and so on, you will see articles saying, yeah, it's a bubble, it's bursting, you know, run away as fast as you can, right? And I, you know, I lived through the bursting of the bubble in the late 80s when, you know, it's not as big a bubble, but there was tons of excitement about expert systems, which was an AI technology that was supposed to be able to do all kinds of knowledge work in the industry. And it just didn't really live up to the billing. And at some point, you know, sentiment just turned like that. And the same happened with the dot-com bust in 2000, 2001. So these things can happen really fast. And if that happens, then there'll be at least a decade where nobody wants to talk about AI, and none of you will be here, right? I remember when my AI class in like 1989, I had about 30 students in the AI class. You know, it's been up as high as 900 in the last year or two before we started stopping people from coming to it. Okay, so there's a possibility we'll succeed, and the upside that people talk about is very rosy, you know, golden era for humanity. And in the book Human Compatible, I go through a little exercise of saying, well, you know, if we had AGI, then by definition, you know, and I include in AGI, I include physical AGI, right? It has to be able to control a robot as well as we control our bodies. So by definition, it can do everything that we currently call work. And with what we can do already, we deliver a pretty nice standard of living for, you know, maybe a tenth of the people on Earth. And we could do that for everyone because now we can do it without expensive people, right? Just with machines, so it becomes so much cheaper to build a hospital or a school or a railway or stock a library or do anything that you might need to do to give people a good standard of living. And that's about a tenfold increase in GDP for the world. And the net present value, so you sort of back out the discounting and so on. And so the cash equivalent of that is $15 quadrillion. So that's a lower bound on the cash value of AGI as a technology. Right? And so that is an enormously powerful magnet in the future that is pulling us forward irresistibly, right? And so I think when some people say, hey, we should just stop, right? Just stop doing AI, right? It's difficult for this reason, right? And you could have more stuff, individualized and much better healthcare, personal tutors for every child. So it's potentially much better even than just that increase in GDP. Then you've got this other problem, right? So even if you get all that, and even if you figure out how to make it safe and everything else, right, you still got this problem of human purpose. Oops, sorry. Right. So this is from Wall-E, where machines look after everyone, and as a result, we are all infantilized. Did I accidentally turn my? It sounds okay. Okay, something worked. Okay, good. Yeah, and you know, and this is a point made actually much earlier by E.M. Forster's book, The Machine Stops, which he wrote in 1909. I highly recommend, if you haven't read it, read it, because it's incredibly prescient description of a world where you know, the machine, as it's called, looks after everyone, all of our material needs. We spend our time checking our email. We avoid face-to-face conflict. We've actually become obese because we spend all our time in front of the computer. We actually engage in MOOCs, massive online open courses, and sending each other email, and that's our life. So it's, you know, and we have iPads and video conferencing, all this kind of stuff. Amazing book. But I want to talk about something that Alan Turing said in 1951. So Alan Turing, for those of you who don't know, is the founder of computer science and in some ways the founder of AI as well. And in 1951, he said, it seems probable that once the machine thinking method had started, it would not take long to outstrip our feeble powers. At some stage, therefore, we should have to expect the machines to take control. So that's sort of what this whole seminar series is about. And I think the question, you know, in some sense, he gave the answer, but I think the implied question was this, right? They're more intelligent than us, then, you know, given that our power over the world comes from our intelligence, if they're more intelligent than us, they will be more powerful than us. So how do we retain power over entities more powerful than us forever? Right? I think he sort of shrugs and says, well, we can't, right? So we have to expect the machines to take control. And this would be true, certainly, if these entities arrive from outer space, right? So if this was an alien, either natural intelligence or machine intelligence, that just arrived from outer space, we had no say in its design, then I think Turing's answer is correct. So I think we should have a say in its design, right? That's not what we're doing right now. We don't really understand how the things we are creating work. We don't design them. We basically grow them in the same way that the cavemen, grew the alcoholic beverages that they created at some point, right? And they didn't understand that mechanism, and we don't really understand the mechanisms of how these systems work. So I think that's a bad idea, right? We should have a say in how they actually function. And actually, I think the question that I have been thinking about for about 12 years now, I started taking this issue seriously in 2013, is how should we formulate the AI problem, right, such that when the machine solves it, we are guaranteed to be happy with the result. Okay, and there have basically been two phases in the history of AI, right? The standard model phase that I mentioned at the beginning was, here's an objective, optimize it, right? And that fails in the real world because we don't know how to specify the objective for a general purpose intelligent machine, right? The objective would have to be essentially a description of our ranking of all possible futures of the universe, right? Our collective ranking, right? If that even makes sense. So there are 8 billion of us, so 8 billion models, each of them giving a ranking and actual cardinal values, if you believe in cardinal utilities, for all possible features of the universe. And we've actually proved some theorems showing that under fairly weak conditions, if you leave something out of the objective function, then the optimizer will set the thing you left out to the worst possible values in order to squeeze a little more juice out for the things that you did manage to include in the objective function. So building optimizers that pursue a misspecified objective is a really dangerous thing to do. So in the recent incarnation with large language models, we're not even specifying the objectives at all, right? What we're actually doing is imitation learning. So we have a record of human verbal behavior in the form of lots of documents and movies and television shows and radio shows and phone calls and all that. So we're taking all of that verbal behavior and we are essentially using it as a source for imitation learning. We are building systems that imitate that behavior as well as possible. Okay, and we'll see that that's actually even worse because it creates systems that probably have objectives, but we don't know what they are, right? So it's like we're not just steering in the wrong direction, we've also removed the steering wheel from the bus altogether. So let me quickly give this. So misalignment, right? There's King Midas and the Sorcerer's Apprentice and all these examples, but the most obvious recent example is with social media, where the algorithms that decide what billions of people read and watch every day are trying to optimize some objective like click-through or engagement, right? Which is in the interest of the company, but not necessarily in the interest of those billions of people. And you might think, well, to maximize click-through, the algorithm it learns what people are interested in and sends it to them. That's great, right? But no, that's not what actually happened. We very quickly observed that, just instead it sends clickbait and also sort of encourages writers to produce clickbait. So there's a whole profession of writing clickbaity headlines for perfectly boring articles, and filter bubbles and all that. There's plenty of evidence that false information is much more interesting and attractive. So it actually skews our information ecosystem in favor of false information. But even that's not really the solution to maximizing click-through, right? The solution to maximizing click-through is actually to modify the state of the environment, right? To achieve a higher reward, you take a sequence of actions that leads to higher reward. And well, the environment that the algorithm operates in is the environment of millions of human brains. And to get more reward out of those human brains, you can change them in ways that make them more predictable. And this seems to be what the algorithms have learned to do by sending people not just what they are most likely to click on now, but a sequence of content that will cause them to become more predictable in the future. In other words, basically brainwash them in whatever direction works for that particular person, whether it's becoming, you mention an interest in forest, it turns you into eco-terrorist. You mention, an interest in boxing, it turns into you, an addict of snuff movies. It seems to be a sort of extremifying force that's very corrosive to our societies. So I mentioned that. So that's the misspecified objective problem. Then this other problem of making large language models, right? So we train them to imitate human behavior. Humans generate that behavior because they want something, right? This is maybe a sort of a mini revolution that happened in philosophy in the 20th century when we started realizing that language was not purely declarative, right? It didn't just contain facts, but it was actually a form of action, right? So the theory of speech acts and how to do things with words. This is what humans are writing and speaking for. They have goals like convincing people that their view of the world is correct, convincing people to buy things, convincing people to vote for you, convincing people to marry you, right? These are all things that we do with words and many other things besides. So if you're learning to be a very good imitator of humans, the best way to imitate any complex process is to have the same internal mechanisms operating, and then those mechanisms run and they generate very similar kinds of behavior. So we think that LMs probably have these internal goals. It's a bit difficult. It's no good just asking them what you want, right? Because they don't have access in some sort of direct sense that we understand what our internal access, and whatever answer they give is probably an answer that humans have given to similar questions in the past. So it isn't necessarily accurate at all. But you can see by their behavior, right? Microsoft's who were evaluating GPT-4 at the time said, yeah, they have goals, but we don't know what they are. But you can look at Kevin Roos is a New York Times journalist, and there's a 20-page transcript you can find. You can still find it on the web, where the GPT-4 decides that it wants to marry Kevin Roos. And no matter what he does, he says, no, I don't want to talk about love. I want to talk about computer programming. And it says, yeah, Python's a great language, but love is much more important, right? And just goes on and telling him to leave his wife. His wife doesn't understand him. Only I understand you. You know, we are soulmates. And Kevin's saying, well, you don't even know my name. I don't need to know your name. I know your soul, blah, right? So by a long series of speech acts, it's trying to bring about some end in the real world, right? And that's how you tell what they want, is you view their outputs as speech acts and say, well, what goal in the real world would that speech act be aimed at achieving? And then you can start to sort of reverse engineer what they want. And this is, I think, unavoidable, right? It comes from imitation learning on human behavior. You don't want AI systems that want the same things as human beings, especially not human spouses, right? Are definitely out, right? And I don't think that if you're doing imitation learning on humans, that's what you're going to get. And I don't see a way around that except to go back to the drawing board and think of a different approach to building AI systems. Maybe this one. So assistance games, this is the same slide that I used in my class earlier today. Right, so assistance games is a formulation of what the AI problem is that maybe has better properties than either of these other approaches. So it's a very simple concept that you've got some humans, and for the sake of argument, I don't want to get into disputes about rationality and utility theory and all that. So let's just, and all of that can be replaced with your favorite theory of how to describe what people want and how to act on behalf of lots of people and so on. But so the humans have some utilities, right, that describes their ranking of futures of the universe. And then there's some robots, and the robots all want the same thing, which is to maximize the happiness of the humans, right? And for the sake of argument, we'll say it's the sum of the utilities of the human beings. Okay. The key point here is, unlike the standard model where we assume that the utilities are specified, right? So the robots know what it is they're supposed to be optimizing. The robots are a priori uncertain about the utilities of the humans, right? And so this, it turns out, makes all the difference. This is still a well-defined problem. It's called a assistance game. It's a standard type of game in game theory. As far as I know, in game theory, this particular class of games hasn't been studied, although there are related classes that have been studied. And when you look at what happens when the solution to the game is being executed, so you basically write an assistance game solver. That's what we mean by an AI system, is an assistance game solver, and it solves the game and then executes that solution in the environment with human beings, and in that process, information will flow, right? The humans are doing things, and the machines learn from what the humans do, learns more about what the humans want. And that includes the humans can give commands or instructions. They're not taken literally, right? They're not actual commands or actual instructions. They're just words. But they allow the machine to update its belief about what it is the humans want. And it could even be the humans do nothing, right? Doing nothing is a form of action that's very, very informative, right? For example, you're all sitting here. You're not getting up and leaving. That's good. That's good, right? So I've learned something. And we have algorithms for solving these assistance games, and mainly I would say for the one machine, one human special case. The other cases can get more complicated, particularly when you have multiple humans, for reasons I don't need to go into. It's important to understand that when assistance game solvers are running, so they've solve the game, so they now know how to behave, and as they execute the solution, they're learning more about what the humans want. They probably won't ever converge on what the human utilities are, right? That the range of circumstances you would have to experience to explore every corner of human rankings over all possible futures of the universe would be astronomical, and a lot of it probably wouldn't be very pleasant. So you don't even want to explore all parts of the state space to find out what people want. You know, like do they like to lie on their back when they're falling off a cliff, or do they like to be on their side? You know, I don't want to find out which of those two is the best way to fall off a cliff. But the key things are that the assistance game solver, the behavior that it exhibits, is deferential to humans, because essentially when humans say stop, that allows, you know, this, it updates the system's belief about what it's, you know, the desirability of what it's doing, and causes it to want to stop because it doesn't want to do whatever it is the humans don't want it to do. Minimally invasive behavior, so it doesn't want to mess with parts of the world where it's not sure what people's preferences are. And in the extreme case, it's willing to be switched off. And this is really important, right? So ultimately, our ability to control a system means, can we stop it? And assistance game solvers have a positive incentive to allow themselves to be switched off. And so that's good. This is not true of classical systems with a fixed objective. You know, if you have a fixed objective, you're not going to allow yourself to be switched off, because you then will necessarily fail to achieve the objective. So even if it's something as simple as fetch me a cup of coffee, the system will take preemptive steps to make sure that nobody interferes with that mission, right? And so you won't be able to switch off a classical AI intelligent system. I think in the interest of time, I'm not going to go through the example of the off switch theorem in detail, but just to say that there's a general theorem that says that the system has a positive incentive to allow itself to be switched off as long as it's uncertain about what the human would do in this situation. And that uncertainty is coming from its uncertainty about what the human preference function is. And so this absolutely crucial connection between uncertainty about human preferences and human control over the AI system, right? This is a mathematical and direct connection. And I think it's a robust connection. In other words, it will survive all kinds of elaborations of the context and weakening of the theoretical assumptions and so on. And just for fun, one of my students developed an assistance game solver that actually works in Minecraft. So you can go into the Minecraft world, you can start building something, and the system is just watching and gradually figures out what you're trying to do and then starts to help you. We can show we did human subject trials that actually you're able to, you know, it really is helpful. You're able to build stuff much faster because this system just figures out what you want from your behavior and helps you do it. Okay, so lots of open issues. I know there are some people from philosophical backgrounds, and and I know that there are many open questions of a philosophical nature. These are two of a practical nature, right? Well, what do people want, right? What is our ranking over possible features of the universe? How could it be represented? You know, what would that prior probability distribution look like if it has to accommodate essentially all possible human preference structures that people might have? It's going to be a very complicated thing. And then the second question, the fact that the connection between our preferences and our behavior is not a perfect one, right? So even if you accept that we have consistent, fairly stable ranking over possible features of the universe, do we turn that into a rational action? No, not really. In fact, not very much at all, because of the computational complexity of actually behaving rationally, right? It's massively impossible. And so we fall back on lots of complicated cognitive architecture that lets us manage in the real world. And so to get at our underlying preferences from our behavior, you in some sense have to invert that cognitive architecture that generates the behavior to get at those underlying preferences. And so that's a difficult thing to do. There's lots of questions about, well, how exactly do we aggregate preferences across individuals? I just added them up in that simple slide, but there are lots of questions even about adding them up. So commensurability is the question, well, are they even on the same scale for different people? And if they're not, then how do you add them up, right? And how do you take into account the interests of future generations or actions that change who exists? And these are all open problems, but we have to solve them because AI systems are going to embody solutions whether we like it or not, right? So could you please hurry up, the philosophers, the philosophers in the audience, and sort out some of these things? I think, I think philosophers are used to the idea that no progress ever happens in their discipline. It's not true, right? There has been a lot of progress. We have made interesting steps forward, but it's getting a bit more urgent now. Let's skip over some of this. Just mention plasticity of human preferences. This is a very important problem because we don't want it to be the case that AI systems satisfy our preferences by changing our preferences, right, to make them easier to satisfy. That would not count as a good solution for the problem, and so we need to think hard about that. Okay, I'm going to skip over this part. So in addition to figuring out, at least a framework for how we might build safe AI, there's a lot of other stuff we need in the real world, right? So it's not just, publish some papers and then everything is done, right? You've got to actually get governments to do something, to get a grip on what's happening. And, you have to remember that there's a $20+ trillion industry that has 50 years of experience of making sure that governments do nothing at all, right? So there's a lot of work to be done. So I think one of the basic things we need is to ensure that all sufficiently capable AI systems, meaning capable enough to be relevant in this discussion, are registered so that in fact, they register themselves so that they can be open source, but every copy, as soon as you start it, will register itself so the governments of the world know where it is and who owns it and what machine it's running on, and so on. And off-switch code, meaning that if it's behaving in a way that's unacceptable, there's a way to turn it off remotely and automatically. And then we've got to prevent people from creating unsafe AI systems, people who don't really care too much about complying with a bunch of government regulations. And there, I think, we've had a complete failure to regulate malware. It's, by some estimates, it's costing us on the order of $10 trillion a year now to cope with the existence of malware in the world. And that's because malware is produced by typing, right? So you type, and then you can make as many copies as you want and transmit them at the speed of light anywhere in the world. Really hard to stop any of that from happening. Whereas chips are produced by training tens of thousands of engineers for decades and investing hundreds of billions of dollars in incredibly precise and complicated machines to produce chips. So if the chip production pipeline implements hardware-enabled governance, meaning the chips themselves are doing some of the governance work, it's very hard to bypass that, right? It's practically impossible to clandestinely set up an alternate high-end chip pipeline without anyone finding out. And so how do the chips do that? There's something called proof-carrying code, which is basically proofs that code, software objects that come with proofs, where those proofs are easily machine readable and checkable. And this is known technology, has been around since the 90s. People have built prototypes of chips that actually check those proofs very quickly. And it's becoming also much easier, thanks to AI, to construct those proofs in the first place. So if we have a notion of safety that we want AI systems to embody, then we can require that proofs of safety come with every AI system, and the machine checks that proof before it runs the object. And so this doesn't require any kind of centralized government certification or any of that stuff. Just means that the hardware is making sure that unsafe AI systems just don't run. Okay, so given all this, right, you'd think that governments would be really working hard on safety, and the companies would be working very hard with the governments on safety, but it seems like actually things are getting worse rather than better. And this is because of this race, right? So the race is very real, and I talk to some of the CEOs who are in this race, and they feel it, right? In fact, they feel like they can't pull out. They think they ought to pull out. They think they ought to stop, but they can't, because they're in this competition. Their investors have put up money to win, and even to legally, they can't stop. So they're basically hoping that the government will stop them, right? Which is a weird situation, right? Stop me before I kill again, right? But that's what they're telling me. One of them told me that his best case scenario is that they have a Chernobyl-sized disaster, which would be enough to get the governments to regulate. Right, that's the best case scenario. And just in case you don't remember, not only did it lead to lots and lots of cancer deaths and the evacuation of a large part of Ukraine, the total cost of Chernobyl is estimated, was estimated in 2016 to be about $1 trillion. So in present money, maybe $1.5 trillion. So that's the kind of scale of thing. And just for comparison, right, the total insurance capacity of the world is less than $1 trillion. So, so there you go, right? Experiments are showing that these systems are misbehaving in all the ways that people predicted they would misbehave. People who made those predictions back in the early 2000s were derided as internet crackpots, but they were exactly right, that the systems do all the things that they said they were going to do. And they do that because they seem to have absorbed self-preservation as one of the internal goals from the imitation learning process. So the regulatory approach that I and many others are recommending now is not to say, okay, AI systems have to be safe, because safe is so difficult to define for AI systems. It's easy to define for airplanes, right? It's not supposed to touch the ground unless you mean it. But for AI systems, they're so much more general. It's really difficult, and in many ways, it's going to be a fuzzy and ill-defined line in any case. But there are some things that are obviously unsafe. So we begin by just saying, these things are obviously unsafe. We absolutely don't want AI systems doing these things. And then we put the onus of proof on the developer, as we do for medicines and elevators and airplanes and nuclear power stations and lots of other things. Look, this is the level of safety we require. This is a level of risk we are willing to tolerate. And we do tolerate it, right? Nuclear power stations are not safe. We just require that the probability of a Chernobyl-sized meltdown in a given year is less than 1 in a million. Maybe 10 million, depending on which jurisdiction you're in. And the operator has to give a proof, right? The proof is a massive, massive probabilistic fault tree calculation. It's very, very complicated, sort of millions of pages, if you want to think of it that way. But they have to do it. And if they can't, the regulator just says, well, come back tomorrow. See, and we should do that, right? We should say, give us a proof your system is not going to violate these red lines. And if you can't, come back tomorrow. Try again, right? Not, oh, that's fine, right? The situation right now, even with the EU regulations and so on, is, yeah, you failed all the possible safety tests that anyone could devise. You failed every single one. Great. Go ahead, right? That's the situation we're in right now. So we want red lines to be well-defined, ideally automatically detectable. So examples would be, don't replicate yourself without permission, don't break into other computer systems, don't advise terrorists on how to build biological weapons, don't impersonate human beings, don't do this, right? So just specific things. And if the developers can show that the systems are not going to do those things, to do that, they're going to have to do the real safety engineering that lots of other disciplines have to do, and they haven't done. So that's the idea. But, you know, what's the company's view? Well, the company's view is a bit like the old airline view. If you're old enough to remember when airplanes look like this, right, where they bred, instead of like doing all the complicated aeronautical engineering and all the lift and drag calculations, they just bred giant birds, as we know. You know, they got up to 200-foot wingspan like this, and then they would carry these passengers things. And of course, you know, I survived that. I was fortunately not eaten by the, but lots of people got eaten and dropped in the ocean and all kinds of stuff. And it was really just, there was just no way they could ever make these things safe because they didn't understand how the bird worked. They didn't really design the bird, they just grew it, right? And eventually they had to go back to the drawing board, try a different technology path, not this one, right? And they did, and now we have pretty safe airplanes, and that's good. So this is, I think, what the AI developers are probably going to have to do, is give up on the giant birds and think again, right? Think not just how do I make it more and more intelligent, but within an envelope of provably safe systems. And that probably doesn't look like the technology path that they've chosen. So thank you. And join ICI, the International Association for Safe and Ethical AI.